Every day, tens of thousands of airplanes carry millions of passengers around the world, soaring through the skies thanks to some of the most advanced and precisely engineered machines ever created, jet engines. And although they appear simple on the outside, just big metal cylinders hanging under a wing. Inside them is a world of microscopic precision, extreme temperatures, spinning parts moving faster than a bullet, and engineering tolerances so tight that even a hair-width error could cause catastrophic failure. And today on the How Factory, we're taking you inside the incredible process of how modern jet engines are assembled with microscopic precision, from raw materials to fully tested power plants, ready to lift a 200-ton aircraft into the sky. It all begins with a design phase lasting years, where aerospace engineers develop digital models of the engine with thousands of individual components, with each one tested virtually using computational fluid dynamics, thermal simulations, and stress analysis to ensure it can withstand temperatures hotter than molten lava and rotational forces strong enough to tear metal apart. Once the design is finalized, factories begin producing the engine's core, which includes the compressor, combustor, turbine, and shaft. The materials used here are not ordinary metals. They are nickel-based superalloys, titanium composites, carbon fiber laminates, and ceramic matrix materials capable of surviving above 1,500 degrees Celsius, temperatures that would instantly melt steel. These alloys are cast, forged, or grown into single crystal turbine blades, meaning the metal has no grain boundaries so it won't crack under extreme heat. Creating one turbine blade alone can take several weeks, involving precision casting under vacuum conditions, controlled solidification, heat treatment, and chemical etching to achieve perfect aerodynamic profiles. Once each blade passes initial inspection, robotic coordinate measuring machines scan every surface down to microns, thinner than a bacteria cell, to ensure it meets exact specifications. Meanwhile, the compressor discs, fan blades, casings, and shafts are produced using 5-axis machining centers, electron beam welding, and additive manufacturing, 3D printing technology that allows engineers to build complex internal cooling passages impossible to form using traditional methods. After machining, each part is polished, coated, and inspected for microscopic cracks using X-ray imaging, ultrasonic scanning, and fluorescent penetrant dye that reveals imperfections invisible to the human eye. With thousands of parts cleared for assembly, the engine build begins in a factory environment that feels more like a scientific laboratory than an industrial workshop. Jet engine assembly rooms are temperature-controlled, vibration-isolated, and kept extremely clean because even a tiny metal shaving left inside a component could cause engine failure later. Technicians wear lint-free uniforms, and tools are accounted for with digital tracking systems to ensure nothing is left inside the engine. The assembly process begins with the main shaft, a carefully machined steel or titanium rod that runs the entire length of the engine. Technicians install bearings capable of spinning at over 10,000 RPM while supporting enormous loads. These bearings must be perfectly aligned within microns. Otherwise, the shaft will vibrate and cause catastrophic damage. Next, the compressor section is assembled. Modern jet engines use multiple compressor stages, sometimes up to 14, each one consisting of rotating blades and stationary vanes. The blades compress incoming air to more than 40 times atmospheric pressure, which dramatically increases its temperature before entering the combustor. Technicians slide each disc onto the shaft, securing them with precision bolts and locking mechanisms. Every blade is weighed and balanced individually, ensuring the entire rotor spins with perfect smoothness. Even the slightest imbalance, barely detectable to humans, could generate vibrations strong enough to tear the engine apart at full thrust. Once the compressor is complete, technicians assemble the combustor, a ring-shaped chamber where fuel mixes with compressed air and ignites. The combustor must burn fuel at temperatures higher than the melting point of its own walls, so engineers design intricate cooling channels that allow cold air to flow through tiny passages only a few millimeters wide. These channels keep the combustor metal cool enough to survive, and producing them requires additive manufacturing or laser drilling techniques that create hundreds of microscopic holes per second. With the combustor installed, the turbine section is assembled behind it. The turbine is the heart of the engine. Its blades extract energy from the hot exhaust gases, spinning the shaft and driving both the compressor and the massive fan at the front of the engine. These turbine blades endure extreme forces, temperatures above 1,500 degrees Celsius, rotational speeds equivalent to the tip of the blade traveling faster than the speed of sound, and pressures so intense they would shred normal metals. Each blade is fitted with cooling passages, ceramic coatings, and precision fits designed to expand slightly when heated, tightening into place during operation. Because the turbine is such a critical part, every blade goes through multiple quality checks before installation. Technicians record the serial number, weight, and balance of each blade, placing them into exact positions on the turbine disc to achieve optimal rotational harmony. With the hot section complete, the fan and nacelle assembly begins. The giant front fan, sometimes over 3 meters in diameter, draws in incredible amounts of air, more than 1 ton per second, in large engines. Fan blades are made from carbon fiber composites with titanium leading edges, making them both strong and lightweight. These blades must survive bird strikes, hail, and runway debris, so they undergo ballistic tests before approval. Technicians mount the fan blades onto the hub and install the spinner cone. The fan case, made from carbon fiber or titanium, is bolted around the assembly to contain any potential blade breakage during flight. At this point, the engine's outer casing, wiring harnesses, sensors, and fuel lines are installed. Modern engines use hundreds of sensors to monitor temperature, pressure, vibration, fuel flow, and rotational speed. These sensors feed real-time data to the aircraft and to maintenance systems on the ground. Jet engines are now so smart they can predict faults before they happen, allowing airlines to perform maintenance before failures occur. Once assembly finishes, the engine undergoes bench testing inside acoustic test cells, giant, reinforced rooms that can withstand the engine running at full power. Technicians bolt the engine onto a stand, connect fuel lines, cooling systems, and sensors, and start the engine with compressed air. As the engine roars to life, computers monitor thousands of data points every millisecond. Engineers test the engine at idle, takeoff thrust, cruise conditions, and rapid throttle changes, ensuring it performs flawlessly. They check vibration signatures, exhaust temperature profiles, turbine speed, compressor efficiency, and fuel burn rates. Some engines even undergo bird strike simulations using gelatin projectiles to verify safety. After passing tests, the engine is partially disassembled for final inspection, cleaned, reassembled, and painted. It then ships to airplane factories where it's installed under the wing or on the fuselage of commercial jets. But the story doesn't end there. Jet engines require continuous maintenance. After every flight, data is automatically transmitted to maintenance teams who analyze trends. Engines undergo periodic borescope inspections, where technicians insert a tiny camera into the engine to examine turbine blades, combustor walls, and compressor stages without disassembly. During major overhauls, engines are completely taken apart, with every component inspected, cleaned, recoated, or replaced. Some engines remain in service for 20 to 30 years, clocking tens of thousands of flight hours. Behind all this precision lies an astonishing supply chain. Specialized foundries produce superalloys, chemical plants create ceramic coatings, 3D printing labs manufacture cooling channels, machine shops cut turbine discs from solid metal ingots, robotics plants build fan blades, and global logistics centers coordinate shipments so parts arrive at assembly plants in perfect order. A single jet engine may contain more than 25,000 individual components sourced from dozens of countries. From microscopic cooling holes drilled by lasers to turbine blades that must perform flawlessly at temperatures hotter than lava, the process of building a jet engine is one of the most extraordinary achievements of modern engineering. What seems like a simple spinning machine is actually a masterpiece of physics, chemistry, metallurgy, robotics, and human expertise, all coming together to lift millions of people safely into the sky every day. And that is how jet engines are assembled with microscopic precision. This is the How Factory, showing you how the world really works. Don't forget to like, subscribe, and stay tuned for more incredible deep dives into the hidden systems that power modern life.